All right, so I have Thibble's LiBCM board that he sent back. This is the one that lowered his pack down to 10 volts over the period of maybe 10 days. And so I'm just going to test this board out and see what's up. And so the first thing I've done is I've put a high voltage source in lieu of an actual battery pack. And I've added this bypass resistor here. It's a 1000 ohm series shunt so that we can measure the voltage across it. The power draw is so low on here that our instrumentation that's used to measuring in like the milliamps range isn't really going to cut it here. And so what we're going to do is I've turned that external 150 volt supply on, and now what we're going to do is we're going to disconnect this so that all of the power LiBCM sources is going to be dropping across this 1 kilo ohm resistor. And that's going to introduce a burden voltage that I'll just ignore because it's only a few volts, worst case. And this, at this point, is measuring the power consumption of LiBCM in microamps. It's a 1 kilo ohm resistor. We're dividing by 1,000. We're in the 6,000 millivolt range. So right now we're pulling about 4,000 microamps or 4 milliamps because LiBCM is on. So in this state, when you have a 5 amp hour battery here, if the battery were fully charged and then we divided by 4 milliamps, you could see that LiBCM can run in this state theoretically for 1,250 hours, which is 52 days. But, of course, the pack's never there, so let's do something more realistic. Every 10% of state of charge when LiBCM is on will give you 5 days of standby time. So in Thibble's case, it looks like his pack was able to kill itself in like 10 days, and that's because he said that the car started but the 12 volt battery was dead, and it started on the IMA system, which means that the battery voltage was high enough or LiBCM would not have allowed it to start it. And then the second claim was that he then waited another 10 days, and then when he tried to start it, the 12 volt battery was dead again, and the IMA battery was dead again, and it measured like 10 volts. And we looked at that on the video. This is true, a true fact at this point. So basically, what I'm seeing here is that LiBCM makes it really difficult to get the SOC below 25%. Like, the car is regenning really hard when you're there, and you can get it down to about 15%, and then below that, it's just impossible, basically. LiBCM is going to disable assist at that point. And so it's really difficult to start with less than a 15% state of charge pack. And since we're looking at 5 days per 10%, we should have gotten, even if LiBCM didn't turn off, we should have gotten like 7 or 8 days before the pack was at 0% state of charge. And at 0% state of charge, the pack is right around 3 volts. Maybe it's 3.2 volts, I forget. It's not 0 volts per cell. It's 3 volts. And then from there, it'll just plummet off. But the point I'm trying to make here is that something else tanked this here, and I really think it's the 12 volt IMA system. The reason being, and I'll show you this here, LiBCM has a lower power mode. This is all when LiBCM is on. Now, as soon as LiBCM state of charge drops below 10%, LiBCM is going to initiate a turnoff here. And so you can actually actuate this whenever you want by typing in $test6 right now. I mean, this is just, the $test is just so I can add my own code to inject things in it. So when I do that, watch this current gauge drop from 4 milliamps or 4,000 microamps to like 200 or something. And so sure enough, LiBCM has now turned itself off. You can see these LEDs are no longer working. Everything is off except for this power supply stays on. We actually cannot turn this one off, but you can see it pulls 150 microamps. It's very, very low. So let's say your battery gets to 10% state of charge, which is again 500 milliamp hours. So I'll just stay here in SI base units. And so we have 0.5 amp hours divided by 150 microamps. And you can see that it's 3,333 hours to use that last 10%, which is 138 days. So in this case, every 10% of state of charge, which you are guaranteed to have at least 10%, and probably you're going to have 20% because, again, LiBCM does not like the state of charge getting below like 25 or even 30% SOC. So for every 10%, you have essentially 140 days. It's less than that, but 139 days of standby time. So even in the worst case, where we're at 10%, LiBCM is not you know, we would have only lowered the SOC by like 1 or 2% in this case. So the circuitry is working correctly. My big concern was that somehow the circuitry was not working. I do test this circuit in the production test. I have a tester I've shown before where I actually plug all these things in and make sure everything is working. It is working in this case, and so the question is, why did this battery pack get killed? And I believe even more strongly now, because I don't see anything wrong with this board. Of course, I'll run it through that tester I just mentioned. I believe that the 12-volt ignition is not turning off sometimes or intermittently in this car. And the hardware on LiBCM is designed to turn back on when you turn the key on, so that if LiBCM has turned itself off, which it has done right now, that turning the key back on will immediately turn it back on, and that way you don't get a check engine light. So because of that, when the 12-volt ignition is on, LiBCM cannot turn itself off, and therefore it's going to be sitting here in this 4 milliamp mode instead of this 0.15 milliamp mode. And so, we were kind of there. I was saying earlier, at 0% state of charge, the battery's still going to be like 3.2 volts or whatever, but there's not a lot of energy left there, and so the voltage is going to plummet very quickly. My guess here is that LiBCM stayed on because it saw that the 12-volt battery was on, and LiBCM senses that the 12-volt battery is on when the 12-volt rail, when the key is on, when the 12-volt rail hits like 5 volts. And so that battery had to be completely dead, the 12-volt battery, and it probably just wasn't there yet. So LiBCM probably never turned off, and that is probably what killed the battery. So we definitely need to check the ignition stuff. Again, I will run this through the tester, and if I do see any issues, then I will report on them, but this PCB looks just fine to me, especially the one important circuit there to make sure that it was working. So the other thought is that there is actually a bug in the code. I don't believe that's the case. I've tested that pretty well. I will test it again, that it automatically works. I mean, I did, typing in $test6 is kind of testing that out well, but anyway, I don't believe that there is a fundamental hardware issue with LiBCM that caused this to occur. I don't believe that there is a fundamental firmware issue that caused this to occur. I really just think that the key was not turned off because I can't really think of what else would have caused that to happen. So anyway, we do need to figure that out. So I'm hoping that Thibble can play around with that 12-volt system, make sure things are good. There's the 12-volt ignition, which is turned on and off by the key. As soon as you turn the key off, that is immediately unpowered. But the IMA bay has its separate 12-volt IMA. That's actually a relay, and it's just a small relay. And if that relay were to get stuck closed, then the IMA 12-volt would never turn off. So let's look at how you could test for that. So when LiBCM is on, I'm going to go ahead and turn it back on here by just plugging the USB power in, which was not plugged in before. And you'll see LiBCM turn on here. And so now that LiBCM is on, this is the condition your car would normally be in when you have the key off, and the D1 should be off. There's these 4 LEDs, 1, 2, 3, and then 4. And the D1 here, let me zoom in if I have this set properly. Is that, yeah, okay. So D4 should basically be lit at all times. D1 will turn on when you turn the 12-volt key on. So if you turn the car off and you see that D1 is still on, then that would mean that your 12-volt IMA relay is sticking. And there's probably a way that LiBCM can actually figure this out. If LiBCM does not see the 12-volt rail signal being high, if LiBCM does see the 12-volt rail being high, but it's not getting valid data from the MCM, like the engine RPM data, then LiBCM could try and turn itself off because it's not getting valid data. So the question I'm having is, can we prevent this from happening again in the future in firmware if the relay sticks? And I think the answer is yes, that we can literally look at the data coming back on METSI, the METSI bus that the MCM sends to the BCM, and then we could take that data, and if the data is indicating that the engine is an auto stop, then let's say the engine is an auto stop. We just start a timer, we reset it to 0, and then if the engine is in an auto stop for an hour, LiBCM can go ahead and turn itself off, even if the 12-volt rail is on. And that way you're not going to be, you turn the key off, the 12-volt IMA is stuck for some reason, and then LiBCM after an hour is going to say, well, I'm going to go ahead and turn off because this is not a correct condition. So it seems like we can prevent this if that is the behavior, if it's the 12-volt rail that caused this, that we can prevent that. Now the last thing I have to mention, and I know this video is getting a little long, is that there is a parasitic draw associated with the actual LTC 6804 But because there are 5 of these, and all 5 of them would have had to have broken the exact same way because they're each running independently of each other. This is doing cells 1 through 12, 13 through 18, 19 through whatever, right? 13 through 18 and 19 through 24, 25 through 36. These would all have to have the exact same issue to get the cells to be that homogeneously low. They were all like 0.2 volts a piece. And Thibble verified that when he pulled the packs out and was measuring, you know, one was at 5 volts and one was at 3 volts or whatever. Those are basically the same values or whatever. So if you had 12 cells that were killed, you know, 12 cells were at 0.0, that'd be really obvious. Hey, look, if cells, what is this, 37 through 48, 37, yeah, if cells 37 through 48 are at 0 volts and all of the other ones are at, you know, 3.5 or whatever, then yeah, this IC itself was defective and that's what broke it. And that's not what happened here. But the current draw from these LTC 6804s when they're off is very, very small. It's in the data sheet, I don't know where it is, but it's probably an order of magnitude of less than this, the 150 microamps. It's like 10 microamps or something. I'll look it up, but this is not what killed it. The BMS portion is not what killed it. And it seems like the hardware portion is working. We've just tested it. We'll run it through the gauntlet. I really think this is something else in the car. And I really think that that something else is the 12-volt rail. So as always, thanks for watching. These things kind of suck. You know, Thibble here is now out, you know, 2 18S modules. And I'm out by proxy the 12S module, but I feel bad about it. So I'll take the hardware at least from all the dead ones. And maybe we'll do some long-term testing on those damaged cells. I just realized I'm still zoomed in, sorry. Those cells that Thibble's sending me, I'm never gonna put those in a car. Like, they're gonna get X'd out immediately, but maybe we can do some long-term testing and on lots of them. They will always be dangerous, so I'm not really sure what that testing would yield as far as actionable data, so it might not be worth it. But yeah, sorry, I've already said it. Thanks for watching.